In this video, we're going to have a look at these two words, bonding and structure, and really try to get to grips with what the difference is, because they're often used interchangeably and they're often used at the same time in a question, and therefore we don't really think about what the difference is and what it can tell us about the properties of substances, what predictions we can make. So, structure and bonding. What is the difference? If a question's asking us to talk about both structure and bonding, what sorts of things should we be discussing? So it turns out there really are still, even at A level, only three types of bonding: metallic, ionic, and covalent. So these are hopefully not new terms. And out of all of those, the majority of those structures are actually giant lattices. There's only two types of structure. So you can either have a giant lattice arrangement or you can have simple molecules. So there's really actually, if you look at this, there's only four options that you can have. You can have metal elements. Metal elements don't really form compounds with other metals. We call that an alloy. They're all going to be metallic. Non-metal elements, such as sort of chlorine or hydrogen, will be diatomic and involve covalent bonding, and of course compounds between non-metal elements. And then at GCSE we're very much stuck in this idea of ionic compounds only being made between metals and non-metals. In reality, what we really want to be thinking about is just the side of the periodic table that the elements come from. So the metals are all on the far left, the non-metals are all on the far right, and what we're looking for an ionic compound is just a difference between an element on the left and an element on the right combining together. And the reason that you will get ionic bonding then is because they have a large difference in electronegativity, and so any electrons will be attracted very strongly towards the non-metal with the higher electronegativity value. So it's more about difference in electronegativity, which is why in fact there are some instances of metals which form covalent compounds. Those metals will be metals that have relatively large electronegativity values themselves. So they will be metals towards top row of the periodic table, not 1+ ion, so 1+, anything that's in a 1+ ion does not have enough protons in its nucleus to really attract electrons. But as we move across, beryllium is an example of something that we might consider a metal because it's in group 2. Actually, because it has 4 protons in its nucleus, if it were to lose 2 outer electrons, it would basically have 4 protons and 2 electrons. That's an extremely positive ion. So actually it would not form an ion, it would end up withdrawing electrons back towards it and sharing them, which is why we use beryllium as an example of a linear compound making 2 bonds, and that's it. Aluminium can also make covalent bonds. It depends on what it's reacting with, and there's going to be a question about that, not explaining it particularly, but about the different compounds of aluminium. So aluminium, if it's with an element that is not so electronegative, will probably be covalent. If it's with a very electronegative element such as fluorine, it will tend towards ionic, because the fluorine will be able to attract the electrons all the way over to its outer shell. So the real difference between ionic and covalent is really you looking at how much difference in electronegativity that there is. So that is our bonding. The electrostatic attraction between charged particles. That's what bonding is. That's what all type of chemical bonding is. In fact, that's really all types of many things that we explain. When we talk about ionization energy, we're talking about the attraction between the outer shell electrons and the nucleus. When we talk about redox, we're also talking about how easily a particular atom can attract electrons or have electrons taken away from it. So all these concepts are just to do with charges and how attracted they are to each other. Intermolecular forces, as we'll see in the video about intermolecular forces, are also all about attraction between charged particles. So although there's different types of bonding, really we're just identifying what it is that is the charged particle. And structure, remember there are only two types. So it's either a lattice or it's a simple molecule. There are some variations among molecules, but that's basically all there is. So looking in a little bit more detail, we're going to look at what the attractions are between. So we're going to look at the common structures that we know, metallic, ionic, etc. And we're going to look at what it is that's being attracted to what. So all bonding can be described as some sort of electrostatic attraction. So we would have attraction between, and then we need to say what it is. So in a metal, we have our delocalized electrons in our sea or cloud, however you want to describe it, and they are attracted to the metal cations, and the reason they are cations is because they have lost their delocalized electrons. So there is an attraction there, and that is a giant structure because that attraction goes all through the lattice. Sodium chloride, an example of an ionic compound here, and so it's hopefully fairly obvious what the attractions are in an ionic compound. They're between oppositely charged ions. And again, that goes all the way through the structure. It's not unique to one sodium ion and one chloride ion, so we have another giant structure. In covalent, although there are two types of structures, so we can have simple molecules or lattices, our definition of a covalent bond remains the same, whether it's between just a small group of atoms or in a giant structure. We still need to describe it in terms of attraction, not just sharing electrons. So what is attracted to what? Well, it's a shared pair of electrons, and they are attracted to the nuclei either side. So covalent bonding is quite different in that it's very directional. The electrons are between two very specific nuclei of atoms. That could go on forever if the atom is capable of making a lot of bonds to make a giant lattice. Or it could be just contained within a molecule. So all of our types of bonding, no matter what the structure, are going to be described as different attractions between different particles depending what's present. So explaining different properties is what we're going to look at next. Conductivity. All we need to know to describe whether something can conduct or not is, does it contain charged particles that are free to move? It's not enough simply to contain charges. Everything contains charges. Atoms have electrons in. So in a metal, hopefully it's fairly obvious that yes, because you have delocalized electrons, and that means that they are free to move. So obviously metals conduct electricity in any state. For ionic, the ions aren't free to move in a solid state, but if you dissolve the ions or if you melt them to become a liquid, then the ions can move. And remember, it's the ions that can move, not the electrons. The electrons are all in the outer shell of the ions already. Simple molecular, absolutely no conductivity whatsoever. There are no free ions, there are no electrons that are not either involved in bonding or are in lone pairs on the outer shells of the atoms. Similarly, in diamond, all the electrons are used in bonding. So carbon makes 4 bonds in diamond, whereas in graphite, carbon makes 3 bonds, and so the extra electron can be thought of very much like the extra electron in, say, a group 1 metal. That is why it's delocalized. We know that unpaired electrons are not stable, that things with unpaired electrons, like radicals, will react very, very quickly. So the delocalization is what stabilizes those electrons. So graphite can be very similar to a metal in that respect. That's why the electron is delocalized. Graphite is going to be the only covalent substance that conducts electricity. So if you have other options, such as silicon dioxide, that's going to be like diamond. It's just going to share all of its electrons. Now let's look at melting point. This is one of the most common questions about bonding and structure. How strong are the attractions holding the particles together in the whole thing? That's what we need to look at. how do I go from the particles being held together in a solid to being moving about? And it's the structure that is the main thing that determines melting point. So one thing that we should know, hopefully, is that covalent bonding is the strongest bond out of the three. And therefore, anything that is held together by covalent bonds in its structure will have the highest melting point, such as diamond and graphite. But all giant lattice structures have high melting points. By high, we mean 1,000 degrees, 2,000 degrees. In the case of diamond and graphite, we're heading towards 3,000 and 4,000 degrees Celsius. So we are talking three figures for metals, ionic and covalent. There are some ionic and metallic substances that are a little bit below that, maybe in the 500 or 600 degrees, but they're not around 100 degrees, 200 degrees, etc. In terms of simple molecules then, there are no covalent bonds holding one molecule to another. So it's intermolecular forces that need to be broken in order to melt, or more likely boil, a simple molecular substance. If you look at that little group of atoms and molecules in that picture, the bonds within those molecules are extremely strong. So the bonds holding hydrogen and oxygen together in water are extremely strong, but we don't make hydrogen and oxygen atoms when we boil water. We just make water vapor. So because it's not a giant structure, I don't have repeating bonds all the way through. I just have bonds within a molecule and weak intermolecular forces. And of course, there are loads of questions at A-level about the different strengths of intermolecular forces, but that's going to be covered in another video. So simple molecular substances are always going to have low melting points, by which we mean, well, the melting point's probably below room temperature, occasionally a little higher. So you do get covalent solids, particularly just if the molecule gets really big. So, for example, iodine, lots of electrons in iodine, so that would be a solid at room temperature. However, it turns to a gas immediately when you heat it, so it sublimes, which is always a clue about very weak intermolecular forces. Similarly, a lot of polymers and plastics, they are obviously macromolecules. They're very, very long, and so there the intermolecular forces become more significant, and they may have relatively high melting points, but still nowhere near as high as metallic, ionic, or giant covalent. Solubility. So can the particles form attractions to water molecules? When you dissolve something, you have to pull apart the water molecules, and you have to pull apart the particles in the solid, and then those particles have to get between the water molecules. So to overcome the bonding, you need to be able to make new bonds with water. So ionic substances often can be water soluble, and you're going to do a lot more about the solubility and the dissolving of ionic substances if you haven't already started in the second year of the course when you look at the energy changes involved. They're not always water soluble because sometimes the bonds are too strong in the lattice to break. The reason they're water soluble is water is polar, and the dipoles of water, these aren't hydrogen bonds, these are dipole ion attractions. The hydrogen in this case would point towards the chloride ion, sodium would be attracting the oxygens in water, but it's the same idea. So we can get bonds out there. Covalent substances, water can't break covalent bonds. Covalent bonds are extremely strong, and there wouldn't be any new bonds formed with the water because there's no charges on those atoms if we broke the bonds. So you can't dissolve covalent. Simple molecular, as we know, intermolecular forces are quite complicated, so it depends on whether it can form, probably whether it can form hydrogen bonds with the water or not. And then metallic, can't really consider metallic as being something that dissolves. So as soon as you break the lattice of the metals up, you you're going to end up with metal atoms that have to take their electrons back. So that isn't going to work. So all metals can do is either react with water, in which case they lose their outer electrons and become metal ions, and they become a compound. So that's not a reversible process, that's not dissolving. So if I put sodium in water and it makes sodium hydroxide, that is not, that's not sodium anymore, it's sodium hydroxide. So they can't dissolve. If they don't react with water, then they do nothing. So solubility is sometimes asked about. It's usually a clue for something that's ionic, but don't count on ionic substances being soluble, because we know from precipitation there are loads of ionic substances that don't dissolve in water at all. So it can also be a clue if something dissolves in a non-polar substance that it's likely to be simple molecular. So something that dissolves, for example, in hexane. Malleability, not asked so much at A-level, but could potentially come up. And malleability means we can mould it, so we're asking whether the particles can be pushed past each other without repelling. So it doesn't apply to simple molecular substances, and that's because they're not solids, so we can't mould it in any way if it's not a solid to start with. Most of the time they're liquids and gases. So really, when we're looking at malleability, we're actually comparing just metallic with ionic, and the reason why one of them is malleable and one is not. So if you apply a force to a metal, then you're going to make a layer move past another layer. And with the metals, the delocalized electrons move with the cations as you apply a force. So the attractions stay there, and the whole thing stays together. If I try and do this to an ionic compound, then you'll end up with repulsion that will break the crystal apart. Because if I try and push that bottom layer, then 2 sodiums will come next to each other and 2 chloride ions will come next to each other. There'll be a lot of repulsion, causing it to break and fall apart. So if you're getting a question that asks you to explain things in terms of bonding and structure, or to predict the bonding and structure, then there are just a few things to think about, any clues that you get in the question that will help you. So if you have an unknown compound, but you know if it's a solid or if it has a high melting point, that gives you a clue as to if it's a lattice or a simple molecule. Very high melting points in the thousands must be a lattice structure. If you're really lucky, you will also get some clue about conductivity, such as conductivity in solution is telling us that it's ionic or if it's molten. Conductivity as a solid tells us it's metallic or it's graphite. We'd need more information about that. And you might get information other than state and conductivity if you're trying to compare bonding and structure about solubility. Unlikely to come up so much when you're comparing, say, a metal with a giant covalent or an ionic with a metallic or anything like that, but might come up if you were trying to decide whether something was simple molecular or ionic, because you might get a clue about the different type of solvent that 2 different substances will dissolve in. So that's a little bit of an overview of bonding and structure. You need to mention both when you're talking about melting and boiling points, and you also need to mention energy when you're doing explanations related to melting and boiling points. So for example, an ionic substance would have a high melting point, and that's because you need to break ionic bonds in order to melt the substance, and ionic bonds are strong, require a lot of energy. When it comes to simple molecular, if you're comparing them, by contrast, you would say it has a very low melting or boiling point. That's because you only have to break intermolecular forces, which are much weaker than any of the 3 types of bonding. And that's about it.